All right, now we are going to look at diffusion and a chemical potential gradient. So in the previous section, when we were looking at diffusivity, we're looking at self-diffusivity. And we're assuming that self-diffusivity, D, is random. Right? And so that means that there's no concentration gradient and an atom is going to move in a random direction around the material, but in no net direction because there's no concentration gradient. But now we're going to talk about what happens when we have this chemical potential gradient, right? So that's just an overarching term talking about the fact that we can have a difference in concentration. And so let's at first look at the case of diffusion in the random case. So let's look at random, right? And so particularly I want to look at the enthalpy of migration, right? So before, you'll kind of remember this plot, I kind of plotted that an atom going through those narrow tunnels has to overcome this sort of energy barrier, delta H m star, right? So that's the kind of activation energy. So if my atom is right here and I want to go to the next spot, which is right here, then it has to go up this energy and then come down, right? So it has to have this amount of energy to reach the next site, right? So that means, and this is the random case. So we're going in this case, one direction here. But now let's think about it in the opposite direction. So now we have this atom, and we want to go back to the other place, right? And now this is the vacancy. Well, in that case, the energy barrier is the same, right? So whether you go from left to right or right to left, the energy barrier is still delta H m star, right? So this is random. So any direction you go, you're going to have this same activation energy. So how this is going to change then when we look at imposing a chemical potential gradient. So I'm going to write that over here, chemical potential gradient. So what that's going to look like for this type of curve is we're going to basically, it's going to look like it's tilted. And so I'm going to draw a line like this. And so what that's going to look like is I have a site here, and then I have a barrier, and then it goes down to the next site, and then it goes up to the next barrier and comes down, right? So think about this right here as an atom, and sort of, again, the energy well. So it's equilibrium position. If it wants to go to another position, that's here or here, right? And so we're going to look at what happens in this case. So this slope then is the imposed chemical potential gradient. And so we're going to talk about this in this next slide here. But this is the distance, lambda, from one site to the next. And this is the difference in energy. And so this value that we have here from where the atom sits to the top of this peak, that is going to be delta G m. So again, so here what I've done, you'll notice that over here I was looking at enthalpy. Here I've switched it to Gibbs energy, again, for a more sort of accurate view of what we're looking at. And so what you'll kind of notice here is that in one direction, so if I go from this site to the next one down here, we have to overcome a gradient of delta G m star. But if you think about the other direction, so this value from where the atom is to the top of the peak here, that value is now bigger by this amount, right? So by this amount that we have here. And so that's what this imposed chemical potential gradient does. All right, so we are going to look now at the effect this chemical potential gradient has. So again, if we're thinking about this atom here, it has lowered the barrier to go from this spot to down the concentration gradient, right? Because now that value is here, as opposed to if we go up the concentration gradient from this spot to this spot, it now has to go overcome that same delta Gm value, but also added to it this additional term here, right? So it's increasing the barrier up the concentration gradient, decreasing it, down the concentration gradient. And so what we're going to look at next is the jump rates. So how frequently does it happen in the forward, which is down the gradient, and the reverse direction, which we're going to term up the concentration gradient. And so we're going to look at the jump rates in those two directions, because now with a concentration gradient, it's different. Without a concentration gradient, those values would have been the same. Okay, so just to clarify a couple terms before we move on. So that term, the difference, so this term right here is the difference in energy barrier between those two directions. The lambda term, which we've seen before, is the same thing. It's the elementary jump distance. So that means the distance from one site like this to the next, which is, so this distance here is lambda, and so this distance is also lambda. So that's the same thing. And then the rise over run of this, so basically the slope, right, of this is the difference in the energy barrier divided by the elementary jump distance. So this is our chemical potential gradient per moles. And so that's kind of what you see right here. We can also think about this in terms of a force per atom. So you can also kind of think about it in that way. All right, so here's the two jump rates that we get for the forward and back reactions. So forward, this will look very similar to what we've seen before, but it's for delta G m. And then the back direction, because we have that added difference, we've increased it by this term here, right? So that means that the jump rate is in the backward direction is going to be decreased because that activation barrier has been increased. All right, so what that does then is it changes the rates. And so when we think about the net rate, so forward minus backwards, so that's the net jump rate, that's going to be subtracting the forward minus the backward. And so we can write out an expression of those two by subtracting the two values that we have. And so the expression that you see here, so this is the flux that results. And so what we're looking at is the flux here is the concentration times this drift velocity. And so when I use this sort of drift velocity, what I'm talking, this is the average drift velocity. And so all this is that jump rate that we talked about times the jump distance. So I kind of skipped a step there, but drift velocity is the jump rate times the distance. And so now we have this average ion flux, J, is going to be equal to that drift velocity multiplied by the concentration. And so again, that factor that we have should look somewhat familiar. And so we have now essentially plugged in that drift velocity multiplied by the distance, and then we have the concentration. So we have this term here for the flux. So inside those brackets, so everything that you see inside these brackets up here, this is the diffusivity of an ion, right? We've gone over that before, and so we can simplify that expression down here, right? So now everything inside that bracket is just the diffusivity, so concentration of the ion times the diffusivity over KT multiplied by F. This is going to be the flux of the ion, right? So I want you to sort of, oops, sorry, let me go back. I want you to just look at this a little bit more and just, again, notice this concentration times the diffusivity. We saw that in the previous section come up, as that was the part that was sort of conserved between ion and vacancy. And you're seeing the same diffusivity times concentration term show up here, but here it's related to the flux. And so that's telling us that the fluxes are equal for the ion and vacancies, but again, the diffusivities are not. And so that sort of ends what I want to talk about when we impose this chemical potential gradient, right? Because that's the additional part that we have to think about on top of the random self-diffusion that can occur in a material.